organizations, Nehru Science Center Mumbai, National Center for Science Communicators, Space Geeks and Indian Space Industries Exhibitors. Good morning, ma'am. It's great. I know it's morning over there, and thank you for accepting our invitation and giving us talk during World Space Week. It's a great pleasure to have you, and I'm sure all audience, all of them are excited to attend your talk. And before taking much of everyone's time, I first invite Dr. Siddhivinayak Barve from National Center for Science Communicators to speak few words. Sir, are you there?
Is
this the Nashville, Tennessee
Ah.
Science Center for Science Communications
Yes.
that Rick Chappell helped found?
unmute, ask to unmute.
Rick was a colleague of
Unmute करो,
mine here
unmute करो ना।
in Marshall.
कोस्ट है वो
और ask to unmute करना, उनको पता चलेगा।
Dr.
Hello.
Barve?
Hello.
Yes.
Now I am audible. Yeah.
Yes, over to you, sir.
Yeah.
To speak few words on the behalf of NCSE, and then we will officially introduce today's speaker. Mr. Rastagi, sir,
Indeed, true. Good evening to all the viewers in India, and good morning, madam, from US. This is indeed one of the great times that such online kind of sessions are on for Space Week, which is in commemorating in the world's first satellite launch. To be frank, from National Science Center, Center of Science Communicators, this is a kind of a communication that we need to take it to the world. And to speak into the world of space, Copernicus first discovered that it is Earth which moves around the sun. But still, what is happening today is there are a group of people world over that they still feel that Earth is static. Similarly, Charles Darwin discovered evolution, but still some people till the day believe that it is God's creation. We don't want to get into controversy, but whenever we have to take the progress of the science and then the countries there are, whenever the progress is to take place, science, when the commoner is aware about what are the fruits of science, that fruits of science would lead towards a better kind of understanding of the world. Example, a series of Carl Sagan on phosphor. And it is said that it was Carl Sagan's kind of an intervention in really taking Apollo program ahead. With his articles, with his kind of television presence, people in America were aware about it. Similar kind of a thing about last week, which I am witnessing, and then I'm listening very astutely about all the science programs that are being on this webinar. National Center for Science Communicators is striving to the same thing. Since almost 1997 till the date, over 200 to 300 professional members as the member of this national body, taking science to masses. Same is the aspect of neuroscience, the same is the kind of motto of the Space Week, and Chintamani Pai's organization is also doing the same thing. Here I see Suhas, and here I see Midzi, Chintamani, and Upesh sir is also here. So that is the kind of a mandate of the National Center of Science Communicators. Take science, the print in electronic, in now webinar form, and then aware society about the fruits of science and how science can really lead toward better life, and then betterment of the progress of all the nations in the world, especially in the Corona time. It is one kind of blessing in disguise that we can connect to the best of the speakers world over. But this is a time that we have been confined to our home, and the communication in this form is one of the best kind of tool that is being there. With National Center of Science Communicators, with President Dr. Jayaraman, Secretary was Nice Adam, and then the professional body of members. I welcome Midzi Madam. I really congratulate to Auroral, Chintamani, and all the collaborators in having this space program. And today's topic is all the relevant, all the three talks that we have seen. Applications of space, that is what is very relevant to the commoners, and then about awareness of what our solar system is, And now it is the expert in sunspots and then sun radiations and all with the connection to the solar system. What could be the space weather? New myth, not new, but it is the innovative topic which has the ramifications in the world, which is being little bit problematic with the new weather kind of conditions coming. Any kind of effect, we are really eager to know, and I welcome Madam Midzi and all the attendees. Now the number is almost 52. With this, greeting from National Center of Science Educator, and I hand it over to you.
Thank you, sir. In fact, we have received more than 900 registrations, and people are watching this program from Facebook Live as well.
Yeah.
And with that, I invite Umesh Rastogi sir to officially introduce our today's speaker, who is head of.
Thank you. Thank you, Shri on behalf of the Neuroscience and my parent organization, National Council of Science Museums, also, I extend very warm welcome to all of our audience as well as Dr. Midzi. And just people who are joining this National Council of Science Museum is this organization, a network of science centers in India. And engaged basically in science popularization, and that's why all those activities, this kind of activities, creating scientific temper and making people aware about what is happening in science. We do organize a lot of exhibitions like this. So we are associated with this National Center for Science Communicators, Space Geeks, and our organization, National Council of Science Museum, Neuroscience Center. I take this opportunity now to introduce our distinguished speaker. I know it's a long biodata introduction. I will cut short so that we can listen more to Dr. Adam. She's basically a solar scientist from NASA's Marshall Space Flight Center, which is now housed in National Space Sciences and Technology Center in Alabama. She's a graduate from Georgia State University with a BS in physics and then an MS degree that's also in physics from the University of Alabama. Basically, she got interested in astronomy or sky gazing rather when she used to travel on long drive maybe with her family members and then watching the stars and night sky and then remembering those names. I heard that Ms. learned from the Multi-Universe website that she wanted to be an astronaut, but at that time perhaps conditions were not very favorable and it was very, very difficult perhaps because she has been a woman where she could not find much women, you can say, in the group. So she may be first in many of those aspects and domain. It is really interesting when I was reading all those things about her. She was advised to remain always physically fit because astronauts perhaps is very, very difficult or a challenging task. So she became astronomer and mostly interested in sun, its sunspots and the magnetic field and how this magnetic field are playing the role in a number of sunspots increasing, decreasing, and all associated with that. So she's going to tell us about space weather connections between sun and the solar system. I think with this brief introduction, I will hand over or take this privilege to invite Dr. Midzi Adam to take over and start her deliberation. Over to you, Dr. Adam.
Thanks so much. I'm very impressed that you did some more research on me. I'd like to try to give a little geography here. I'm located in Huntsville, Alabama, and we are about 2 hours south of Nashville, where Dr. Barv is located. And so I will go ahead and get started with my presentation. And we are going to talk about space weather, the connections between the sun which is my favorite thing to study, and the solar system. And I want to point out that this background image was created from a model, from modeled data from NASA's Scientific Visualization Studio. And I would invite you to take a look at some of the resources that are there. And if you just Google Science Visualization Studio, you'll find that there's a lot of images and animations that you can use and that show a lot of the physical processes that are going on. In 1989, a massive blackout left millions of people in the dark for 12 hours. This happened in Quebec and spread through to some parts of the Northeast United States. The auroral oval, we'll talk about that, what that actually is, moved southwards towards the equator, and aurorae were seen in Florida, a very, very rare happenstance. A transformer, a massive transformer, was damaged in the Northeast from geomagnetically induced currents. Talk more about that too. But this transformer is seen relative to a person, so you can see how large it is. And some of the damage that occurred is shown in this image on the right. At the time, there were a lot of issues between the East and the West, the East meaning Russia or the Soviet Union. And there were radio signals from Radio Free Europe that did not get into Russia. What that might have sounded like is here. Now, what you were hearing was a ham radio operator, and his signal was fading with time as the noise level went up. And over time, the noise level began to drop, and the ham radio operator could be heard again. So what caused these problems? Could it be earthquakes, tornadoes, hurricanes, an alien invasion? I don't know. Think about that. What could have caused the problems? Now we're going to pause for a poll. NASA likes to keep track of statistics to try to determine if we're doing a good job. So I've created a poll that I would like for you to answer if you don't mind. And the location of that poll is here. And whoops, sorry about that. If you could open up your browser and go to that website, I would appreciate it. There is
paste a link in the chat box.
Yes, I'm working on that. I am working on that. Let's see if I can find that. I have a couple of windows open here and trying to find everything. There we go. That's the one I wanted to find. Bring that up. And where is the chat? There's the chat. Well, I don't see the chat.
Just beside share screen.
There it is. Okay. So I apologize. I should have had this already ready to go, but too many things going on. Okay, so there is the URL. And if you go to that URL, you should see a question that says, are you male or female, or do you not want to answer that question? And I'll give you a couple of seconds, couple more seconds to answer the poll question. And then we'll go on with another one. Now I'm going to deactivate that question and activate another. And I'm deactivating now and activating another. And this one has to do with your age. What is your age range? Yeah, I'm getting up there. I'm now 67. I just had a birthday last month. And so far I feel okay, although I have to admit COVID has not allowed me to work out as much as I would like. I miss going to the gym. There are 3 more questions in this particular poll, and I'm going to deactivate the age question and activate the next question. Here's the next one. I'd like for you to rate how interested you are in space science. I suspect with this group here, everyone is very interested, but maybe some of you are just curious and aren't sure. What is space science? What is it all about? So let me know what you think about that. And I'm about to deactivate that question and go to the next one. This one is a true false. The sun is a star. True false. For those of you who are participating in this poll, I really, really appreciate it. We're trying to get some statistics, and it has been difficult since we haven't been able to appear in person. And this seems to be an okay way to try to do this. I'm going to deactivate this question and activate the last one in this poll. We're going to get this at the end, just warning you. So aurorae are caused by solar wind particles hitting Earth's atmosphere. Okay, very good. Very good. I'm going to deactivate this question now. Warning, warning, deactivating now. And as I said, we'll be polled again at the end of the talk. So leave that page up, please. Okay. So to remind you, what we were discussing before the poll was what caused these problems. Was it earthquakes, tornadoes, hurricanes, or the alien invasion? Well, of course, the answer is space weather. Space weather caused these problems. Well, what is space weather? What the heck is it anyway? Well, first of all, what do we mean when we talk about weather? What is weather? Well, basically, weather refers to short-term conditions. And the short-term conditions could be temperature, humidity. Is it sunny? Is it cloudy? Is it rainy or is it dry? Is it windy or not windy? And all of this leads to, what do I wear for the conditions, the short-term conditions that are occurring today? How do I respond to my environment? So space weather has some similarities to Earth weather. There are particles that can come from the sun, electrons and protons, and these particles can travel very fast, and they can affect the solar system. And in this way, we have a similar situation to the density to maybe tornadoes or rapidly moving particles, a hurricane. There's not rain, but there is actually precipitation, which we'll see in a minute. So here we have a coronal mass ejection here coming from the sun. And now it's passing Venus. Now it's at Earth. And when it gets to Earth, the solar wind density, as measured by a satellite close to Earth, you can see the solar wind density increases. So these are real data, and they came from the Stereo spacecraft. There were two of them orbiting the sun, and one was ahead of Earth and one was behind Earth. And one of the satellites is no longer working, so we don't have a stereo anymore. But that's how we were able to get these images. And the other one is the wind instrument that's located closer to Earth, and that's where the solar wind density comes from. So in this case, we were interested in conditions close to Earth. And I'll play the movie again, because as you can see, there's always solar wind moving from the sun. And occasionally we have these huge conditions, coronal mass ejections, that can cause shocks and accelerate the particles towards Earth. So we would call these conditions windy, although it's not air moving. Our space weather starts with the sun. Here you see an image of the sun with sunspots. This is the photosphere, what we call the surface of the sun, and the spots are simply intense magnetic field that comes through the surface, the photosphere. And the sunspots can become active, but you don't typically see that activity reflected in the photosphere. You see it in different layers of the atmosphere, and I'll show you that in a minute. But here is a recent image of the sun showing active region 12882. Now, this was a relatively simple sunspot. It developed a little bit more complexity of its magnetic field as the sun rotated it around. But we number sunspots and actually count them, and we label them active regions because they tend to be centers of activity. The sunspots occur in a cycle, and the average time between the two maxima or the two minima is 11 years. So here around 2000, we had a maximum of sunspot activity. And when I say a maximum, all we're doing is counting those sunspots and plotting it on a graph against time. So here at the maximum, there were over 200 sunspots on that particular day in the year 2000, around the year 2000. And I should explain that the jagged line is the actual data, the actual sunspot number. The dotted line are errors on the predicted sunspot number, which is the solid line. And these images, the graphs, were actually created by David Hathaway, who is a former colleague. He transferred to NASA's Ames Research Center in California, and after about 4 years, retired from there. He and his former graduate student Dr. Lisa Upton, have continued with doing this kind of data analysis and creating those plots. And they have their own website where they publish them. So I mentioned that we see the sunspots in the photosphere, but the activity is reflected in other layers of the atmosphere. This is an H-alpha, a hydrogen alpha image from the Big Bear Solar Observatory back in 2014, which was around the time of the maximum of cycle 24. We're currently in cycle 25. And you can see some of the activity reflected in this active region 12158. See how it's brightening, and we would call this flaring. And the flaring can be recognized by an X-ray camera, not an X-ray camera. It's an X-ray detector on board the GOES satellite, which is in geostationary orbit. And so it gives us data 24/7 about what the sun is doing, how much X-ray is being emitted. And so the graph that you see are the X-ray intensities in watts per square meter plotted against time. And on that day, there was an X 1.6 flare. So here's the X range, and you see the top of the red band, which is the X-ray range from 1 to 8 angstroms is seen. And in the 0.5 to 4 angstrom range, the blue is peaked here. So when things like that happen, sometimes there is a coronal mass ejection. Not all the time, but sometimes, more often than not. And you can see it in other wavelengths. So this is actually corona, the top layer of the sun's atmosphere. And this is what that flare looked like in extreme ultraviolet. This is from the atmospheric imaging assembly on board the Solar Dynamics Observatory. And what's happening is the CCD is being overwhelmed. So it was pretty bright. And then flare loops occur. And I see a question in the chat, what causes that 11-year periodicity? We don't know. That's something we're trying to figure out. It's a reflection of what's going on in the convection zone and how the sun produces the magnetic field with the dynamo. But we don't really know. I'll show that one more time. You can see the loops are brightening, and then the major flare comes out. We have another observatory which has been there forever, and it produced that active region I just showed you, produced a coronal mass ejection. And this satellite, SOHO, is a coronagraph, and it's observing in visible light. So that's the light that we see, that our eyes see. And I will answer those questions in just a moment, but let me explain to you what you're seeing on this picture. This is the coronagraph. It's actually a disc. It's held in place by this arm, and it covers up the brightest part of the sun. So it's covering up the photosphere and a good portion of the corona, which is the upper layer of the sun's atmosphere. And this circle in the middle, the white circle, is where the photosphere ends. So the photosphere is what we call the surface. But remember, the sun does not have a solid surface. It's still gaseous. But this is what we see in our sky, because it's producing visible light that our eyes can see. And the X-rays don't get to the ground. The ultraviolet doesn't get to the ground, at least some form of it. Fortunately, our atmosphere protects us from that. So the 11-year periodicity is not caused by the flipping of the magnetic poles. But the magnetic poles do flip with the 11-year cycle. Okay, so let's take a look at what a coronal mass ejection looks like as seen from SOHO. And SOHO is actually in between Earth and the Sun at a place we call the Lagrange 1 point. This is a very stable place where it doesn't have to use very much energy to stay in place. It just kind of sits there. So that is a coronal mass ejection. It's called a halo coronal mass ejection because it's seen to halo the sun. It comes out on all sides. And what that means is that it's headed towards Earth. And I'm going to play it again because you also see all of these sparkles, the snow. And that snow is caused by the electrons and the protons interfering with the electronics on board SOHO. And the CCD camera is seeing the charged particles that come through. And, you know, you can see it comes through pretty quickly. Let's see, 20 to, you know, fairly quickly. It can take days for the main mass of that coronal mass ejection to get to Earth. But there are some particles that travel really, really, really fast, and they can get here in hours. Okay, so we have an effect, or we have a phenomenon called magnetic reconnection, and that happens on the sun and it happens at Earth. When we have a solar flare, magnetic reconnection is actually occurring, and that magnetic reconnection is sort of the driver for the explosion. It's the driver for accelerating the particles. And sometimes those particles do escape from the gravity of the sun, and that's when you have a very large event that we call the coronal mass ejection. And I'll show you what that looks like, or an artist's concept of what that looks like in a moment. And then when the coronal mass ejection reaches Earth, you have magnetic reconnection in the tail of the magnetosphere. The magnetosphere is just the Earth's magnetic field, and it is stretched out because of the solar wind. Remember, it's not an actual wind, but it's the charged particles, electrons and protons, that come from the sun. And that solar wind flows all the time. But when we have a coronal mass ejection, there is a large kick to that, and a density increase to that background solar wind. Okay, so this is the animation. And remember, this is a conceptual kind of a thing. So you have a coronal mass ejection, which is initiated by magnetic reconnection. And it moves through the solar system, passes Mercury and Venus. Then it gets to the Earth. It pushes on the front side of the magnetic field. And then the magnetic field lines reconnect on the back side. And this propels particles, those electrons and protons, but electrons mostly, towards Earth and into Earth's atmosphere. And those electrons collide with... Someone needs to mute. The electrons collide with particles in the atmosphere of Earth, and then those particles give off light that we call the aurora. And this happens in the northern and the southern hemisphere. So I'll play it one more time. And that's an example of magnetic reconnection. I mentioned at the start that the auroral oval would move south. During very, very large coronal mass ejections, this area would move southward towards the equator. So instead of being centered up around the Arctic areas, it would move southward. So then you could have aurora all the way from Canada to Florida. And similarly, that would happen in the southern hemisphere, where the auroral oval would move northward towards the equator if you were in the south. And what I just referred to as the electrons moving, being accelerated towards Earth and interacting with particles in Earth's atmosphere, that is the precipitation that we see that occurs as a result of space weather. So we have a couple of different types of space weather. I mentioned earlier that we can see solar flares. Now, those solar flares are just intensifications of light. And the flares can cause disruptions in shortwave radio. And that would be the cause, a flare would be the cause, or a cause of ham radio fading during a solar flare. And it's short-lived, it comes back pretty quickly. But there are other implications too for aviation and atmospheric drag, because the flare can heat up Earth's atmosphere. Earth's atmosphere expands, and as a result, satellites' orbits can begin to decay. And then we have the charged particle radiation. So electrons and protons with a lot of momentum due to their high rate of speed can impact human space exploration. And these are some considerations that we are addressing as we begin to move from Earth to Moon and on to Mars. It's a very important question. There can be data corruption. There can be damage to satellite electronics. There was a satellite outage in 1998. There was a Galaxy 4 satellite that was impacted. And we don't use pagers very much anymore, but at the time, 40 million pagers were impacted for several hours. And at the time, doctors, especially, were using pagers to stay in touch with their hospitals and their patients. And that could have impacted health quite a bit. So then we have this magnetized plasma. So when these particles, when the coronal mass ejection happens, the coronal mass ejection is made up of electrons and protons, but they're also carrying the magnetic field of the sun with them. And so it's embedded in that cloud of material that comes from the sun during a coronal mass ejection. And that can interact with Earth's magnetic field and cause some GPS signal issues. It can affect power grids, and this ties back to the geomagnetically induced current that I mentioned. The magnetic field of the sun is interacting with Earth's magnetic field, can interact with Earth's magnetic field. And that magnetic field then in the ionosphere creates a current that travels all the way to the ground. And that current then interacts with the ground, causing a current in the ground. And that can have effects on the power grid, as we've seen, the one in 1989. And it can also cause corrosion in pipelines, again, the atmospheric drag, and more satellite electronic damage. So these are some of the space weather effects that I mentioned. You have solar flares, you have coronal mass ejections, you can have interaction with solar cells from the solar flare protons. And then, of course, as I mentioned also, there's the astronaut safety. And as we move away from Earth's atmosphere and Earth's magnetic field, both of which protect us from the major issues of space weather, we're going to have to confront this problem of preparing astronauts for being in space and on the surface of the moon and the surface of Mars without the protective atmosphere and magnetic field. So the summary here, our sun is not a steady, stable, it's dynamic. Things are going on there all the time, even during solar minimum. The sun has an activity cycle of about 11 years. During the maximum of this cycle, the sun is more likely to produce large space weather events, but that can happen at any time. And as a matter of fact, the largest events that we know of have happened on the downside of the cycle. So we're actually past the downside of cycle 24, and we're now on the upside. We're headed up to solar maximum of cycle 25. And those space weather events can produce effects at Earth and can have similar effects on any planet of the solar system that has a magnetic field. So that would be Jupiter, Saturn, Uranus, Neptune. Mars has a residual magnetic field, and so there are some effects there that have recently been measured, and I don't have those data in this talk. Venus does not have a magnetic field, but space weather events have still affected Venus. And the solar wind does tend to strip off a planet's atmosphere. So that's a reason why Mars has such a thin atmosphere. So Earth's magnetic field and our atmosphere protects us from some of the most damaging effects. Now let's go for that poll again. If you joined late, let's see. Let me do this. And this is the, that's the link to the poll. And I need to activate the question. And I am going to do that. We just have a couple of questions here. I'd like for you to now rate how interested you are in space science. And this is a repeat of the first question, which was to rate how interested you are in space science. But that was before my talk. Are you more or less interested in space science? And this can really help me determine whether I've done a good job. I'll give you a couple more seconds to finish that. And I'm going to deactivate that poll question. And the next one. The sun is a star, true, false? Our sun is bright. We get light from it. Fortunately, because we'd be in the dark if we didn't. That light heats up the atmosphere. It heats up the ground. So the sun is a very, very important part of our solar system. I'm going to deactivate that question. And the final question. And before I do this, I want to say one more thing about that magnetic reconnection and aurorae. As I said, the solar wind flows all the time. When we have the coronal mass ejection, it pushes on Earth's magnetosphere and causes the magnetic field to flip backwards, as we saw in the animation, and compress, which creates magnetic reconnection in the tail of the magnetosphere, which is swept backward by the constant solar wind. And then particles that are already in orbit around Earth and that stay in the magnetic field trapped within the magnetic field of Earth are then accelerated toward Earth and impact particles in Earth's atmosphere to cause the aurora. So it can also energize, fill up the Van Allen radiation belts, causing the density there to go higher. So satellites flying through the Van Allen radiation belts have to be prepared for that. So it's really important for us to monitor these events. Okay, so with that, here's the last question in our poll. Aurorae are caused by solar wind particles hitting Earth's atmosphere. True or false? Okay, I took a look at the responses to that question, and I'd like to go back to this. Okay, the solar wind, by the way, that question is still activated, and I think you can change your answers. No pressure. But the solar wind flows from the sun all the time. Coronal mass ejections increase the density of the solar wind and the speed and impact Earth's magnetosphere and any magnetosphere in any planet that has a magnetic field. So the coronal mass ejection is the gases are accelerated by magnetic reconnection at the sun. The particles hit the magnetic field of Earth, and the magnetic field lines squish together. That's a scientific term, squish. And here we have reconnection in the tail that accelerates particles that already exist in the magnetic field around Earth towards Earth. So there are oxygen atoms, there are electrons and protons that already exist in this magnetic field, in Earth's magnetic field. And those are the particles that are accelerated back because they are the ones that are along that magnetic field area. Let's go back here. So here, magnetic reconnection has happened inside Earth's magnetotail. So the particles that are inside the magnetic field of Earth are the ones that are accelerated towards the poles to create the aurora. Lovely. Okay. So I will make just a couple more statements here. The work that I'm doing is sponsored by NASA Heliophysics Education Activation Team. And we do have a webpage, and we're going to be very involved in the upcoming eclipses for the United States. There is an annular eclipse in 2023 and another total solar eclipse in 2024 that crisscrossed the United States. So if you are interested in learning more about those eclipses, there's already a lot of information out there. So that does it. I won't stop sharing just yet, in case there are any images you would like for me to return to. I'd be happy to try to answer any questions.
Thank you. Thank you. Thank you, ma'am, for such a lovely lecture. And I'm sure all the students, enthusiasts who are watching your lecture, they must be really happy to read more about space science and space weather. It was indeed very fascinating lecture for all of us and informative too. Forum is now open for question and answer session. I parallelly went through questions in the chat box, and there was a question: are solar flares predictable?
Somewhat. I would say that they are predictable as a probability, as probabilities, but not you can't say there's going to be a solar flare in 5 minutes. At the moment, we can say there may be a solar flare in the next 24 hours, maybe even in the next 12 hours, but not any more specific than that.
Thank you. And then there is another question. Probably I'll just try to reframe that question. It's just that if we are talking about forces experienced by charged particles, so from where the electric field is coming apart from the magnetic field?
Well, the charged particles are moving. So you have an electron, which is charged, and you have a proton, which is charged. One is positively charged and one is negatively charged, and they're moving. So since they're charged particles and they move, they create a field.
Okay.
And then they interact with Earth's magnetic field. I'm going to put a couple of links in the chat box that you might find interesting. Other questions?
Yeah, actually, we are still getting the questions, few questions. Meanwhile, I have a question. When we talk about magnetic reconnection, so how do we predict at what distance these magnetic field lines reconnect themselves? Is there a way to simulate that, or based on where that reconnection happens, can we actually predict further consequences, the motion of the flux of charged particles at the poles?
That is a difficult question. There are models that can address that issue, but I am not aware of how accurate they are. And it's a very difficult thing to test, because in order to observe the magnetic reconnection, you'd have to have an instrument in place to see it, to measure it. So I know that there are models based on density and the solar wind speed, or the coronal mass ejection speed and density. But how accurate they are is difficult to say.
Thank you. I can see one more question in the chat box. Again, I'll try to reframe it. It's basically about, can we stop solar storm? So how we can even prevent maybe electronics onboard satellites or spacecrafts from solar storms? Are there any upcoming or novel technologies coming up?
There are ways to shield electronics. They call it hardening. It's expensive, but it is done, especially by the military. The scientists are not quite as interested in doing that. Although, if you're going to be observing a coronal mass ejection, you want to make sure that your electronics are going to last for a while. In terms of how astronauts can shield themselves from these effects, there are currently plans for certain types of habitats. So when we see a solar flare, that radiation is already here. If there is a coronal mass ejection that accompanies the solar flare, that can take hours to get here for the fastest, most energetic particles. So that does give the astronauts time to get into an area that is safe. And on the International Space Station right now, there is a safe area located within the interior that, as well as having Earth's magnetic field around them, they can go into that interior location and the atmosphere, because there's still atmosphere up there at ISS. It's not breathable, but there's still atmosphere up there. So the astronauts can go there until the bulk of the material passes by. If they happen to be on the moon and there is a solar flare, then they've been exposed to the radiation, to that electromagnetic radiation. If it's not a sufficiently large solar flare, there probably won't be any interaction. But to shield against the coronal mass ejection and also cosmic rays, they are talking about using either caves on the moon created by lava flows in the past, or using the regolith, the soil of the moon, to create habitats. So you have to be thick enough so that there is not secondary radiation produced, which could also harm you. And the consideration is also trying to do something like that on Mars. Interestingly, if you are going on a long-term mission to Mars, you have to take water. You need water. So water is a very good shield against these particles. So there have been some thoughts of having the crew inside a bubble of water, which would shield them from some of these effects.
Is it because the water is kind of diamagnetic in nature, paramagnetic in nature? Yeah.
I think it has to do a lot with the density. So you've just got a lot of material in between the human and the radiation, and that the water molecules stop the radiation. Probably right. Because of, yeah.
Then we have next question. Is there any way one can link periodicity of sunspot cycle with the nuclear fusion reactions at the core?
Not that I'm aware of. Indirectly, I suppose, because as the nuclear fusion reactions at the core of the sun continue over time, they are depleting the hydrogen that fuels the reactions. And so you have a different composition, and you have more and more helium being deposited in the core, and the hydrogen where the fusion is happening at the core begins to move outward. So indirectly, I suppose that could be affecting the magnetic cycle, but exactly how that plays into, because you have the core, and then you have the radiative zone, and then the convection zone, and it's in the convection zone where you have the dynamo effect occurring that creates the magnetic field. There's probably some correlation between the rotation rate of the sun and the magnetic field. So as time goes on, the rotation rate decreases. And the core, the very center, will eventually get hotter. And so the outer layers of the sun will puff out more. But a direct relationship with the fusion reactions in the core, I'm not aware of any direct correlation.
We have the next question. Are aurora also happen on other planets in solar system?
Well, it's difficult to say because we can't see those other planets easily. But we do know that sunspots occur on other stars. We call them star spots. And we can tell the rotation rate of the star, especially if it has star spots. And so we know that if it's rotating, it's going to be creating a magnetic field. And so there will be space weather. There has been some discussion of extreme space weather at the Alpha Centauri system, which would possibly prevent life from happening on Proxima Centauri, which is the planet in that system that's closest to Earth.
Right. Okay, we have, let me see, there are more questions. Okay, there is one question about solar waves. What impacts it has in the magnetosphere, the solar flares?
Well, the solar flares are intensification of light, brightenings, and they produce we can see, it's not very common, but we can have seen flares in visible light on the photosphere. That happened in 1859, so it's a really pretty rare. That's called the Carrington event and produced probably the strongest space weather that we know of in recorded history. And the only reason we know about it is, well, there are a couple of reasons. It was said that the aurorae were so bright in England that you could read a newspaper at night. But there were the beginnings of technology. Telegraph lines, long telegraph lines existed. And so the ground-induced currents or the currents and the magnetic field in the ionosphere and that came down to the Earth created currents in these long telegraph lines that produced sparks and fires, and they could run off of the current in the ground for hours as this happened. And so that one that was the reason we know about that. But in terms of what the flares do to Earth's atmosphere, they heat it up. And so the atmosphere, gases when heated, they expand. And the Earth's atmosphere expands. And so we can get degradation of satellite orbits as a result. And we can have airline pilots, they have a radiation detector on board. So especially those that fly at higher latitudes, closer to where that auroral oval is, they can receive higher doses of radiation during a solar flare. So at those times, they would lower their altitude and maybe even change their trajectory to avoid that area, which is costly because they use up more fuel if they go lower in the atmosphere. And the other effect, as I mentioned, is that radio communications can be affected. GPS can also be affected, but something called ionospheric scintillation. I see a hand.
Mr. Sudeep? He has, okay, you can unmute yourself and ask your question.
Hello. Good evening, good night, ma'am, good night. I'm Sumit Kumar Bandhavardhan speaking to you. Hello, ma'am, am I audible? Hello, ma'am, am I audible? Hello.
Yes, you are audible. You can ask your question.
Oh, madam, I want to say that I recently came to know from this post of the NASA that Europe space station and that need to prevent the climate change. So, madam, I want to ask you that I think that it is basically change the radiation, something radiation that is harmful or Earth, the environment is polluted due to radiation, some unwanted radiation is coming to Earth's surface right now, but because of some change took place in the total solar system, maybe. So that may be the cause that is the climate change, they can control only the radiation control. That is my questions to us.
Maybe I'll reframe his question. Basically, he wants to know if there is any space weather contribution to the climate on Earth.
But basically, radiation control. The climate change, that can be changed. That change took place. Basically, control the radiation because some unwanted radiation coming to our Earth's surface. Definitely, some change took place in our solar system. So that's why I like to put the question. That is the climate change can be controlled by radiation control only.
If I understand the question correctly, and the audio is not extremely clear, but I believe the question is, does space weather affect climate change? And directly affect climate change as we are seeing it now? No. On a long-term scale, millions of years, yes. Pardon me while I see if I can let my dog out. Sorry about that. The joys of remotely working. Okay, so as the sun changes, its outer atmosphere will expand, and I'm talking millions of years, maybe even billions of years, so that eventually the outer layers of the sun will nearly reach the orbit of Earth. So that will definitely affect Earth. Earth will be unlivable at that time, but that won't happen for, 4 billion years or so. It's something to think about in terms of space exploration. If we as a species want to survive and I would kind of like a lot of our species on Earth, not just humans, to survive, then we're going to have to move off planet. But we have time to do that. In terms of the changes due to the solar cycle over the last 100 years affecting climate, no. There's no evidence.
Thank you, ma'am. So I think we'll stop here. It's time to end the session. And with that, I invite Dr. Vaibhav Rao to officially go for vote of thanks.
Thank you. I have a pleasant duty to give vote of thanks. So first and foremost, I thanks Mr. Adams for accepting our invitations to deliver a talk and making this World Space celebrations a memorable one. And to thanks our organizing institutes. We thank the head of education of Nehru Science Center, Umesh Kumar Rastogi sir, and his team, particularly Rajesh, who has been tirelessly working on the technical aspects in this organizing lectures. We would like to thank Mr. Suhas Naik Satun sir from National Center for Science Communication, and Mr. Dr. Siddhivinayak Bhave sir for being here with us today. And we would like to thank Mr. A.C. Mathu from Indian Space Industries Exhibitors for the constant collaborations in organizing various events and to be part of organizing members of this World Space Celebrations talk series. We have received more than 900 participations, 900 registrations for this World Space Week Celebrations 2021 seminar series. And we would like to thank all those participants who have turned out in large numbers and here with us. And with this, I just want to highlight that Space Geeks is a young startup who is working in the domain of space. And we are associated with all this organization, and we plan to bring out more such events for students and space enthusiasts. So stay connected with us and stay tuned for tomorrow's talk at 4:30 by Khushbu Mirza, which is the last talk of this seminar series. Thank you all for joining, and good night.
Thank you, ma'am.
Thank
Once
you.
again, thank you.
Thank you.
Just one announcement. You can, Chintamaniji, I think we need to tell people about essay contest. Since we have got much more response than we expected, so it's taking slightly more time in announcing the result so that we can do the justice whatever people have written. Okay, so please wait for some more time. I will announce that result also as soon as it is ready. And thanks for being with us, all of you. Tomorrow at what time is the talk?
4:30 p.m., sir.
Evening. Okay.
Yes.
Okay, that's all from us. Yeah, Mr. Suhas and Dr. Barve, if you have anything to say, you are most welcome.
Yes,
Otherwise,
sir.
we can conclude.
Thank you so much, sir. Chintamani, thank you so much.
Thank you. Thank you, sir.
Thank you, everyone.